Welcome back. In the previous video, we started talking about vectors and fields, and we're going to continue on with that. In particular, we're going to study the addition and subtraction of vectors, and we're going to define some terminology. So let's have a look. All right, so the first thing that you need to be aware of is the magnitude of a vector. Vector magnitude. And there are a lot of different terms for this. So we can say magnitude, or I'll just put an equal sign there, meaning that those words are equal, synonyms. Magnitude, or we would say norm, the norm of a vector, or we can say the length of a vector. So you might hear me say all three of those things over the course, and they all mean the same thing. And so we notate this like this. So we'll take a vector, we'll call that vector A, and so notice I'm giving it an arrow, meaning it is a vector, and I'm going to put these vertical bars over it that you might call absolute value when you're not dealing with vectors, but this is meant to be the norm, or the length or the magnitude of a vector. Also, we might just write it like this. Okay, just as a letter. Now, when you take the norm, or the length, or the magnitude of a vector, what you get is a scalar. So, for example, if I had a force like, or let's talk about displacement. If I walked 5 meters, north, and I took the magnitude of that, that's just 5 meters. Right? You leave off the direction. So the magnitude is always a scalar, and it's always positive, actually, or I'll say it's never negative, because it could be zero. So now this is consistent with our notation. If I leave the arrow off, then that means a scalar. So but I'm going to use the same letter to show that that this scalar is the magnitude of this vector A with the arrow over it. So either one of these notations is fine, with the bars or without the arrow. That means the magnitude, the norm, the length of A. A unit vector has a length of, yeah, you guessed it, 1. So if A is going to be a unit vector, then it has to be true that its length is 1. Okay? Now in this case, we reserve a special letter for unit vectors, so we're not going to use that. Right? We're going to use lowercase a, and it's actually always going to be lowercase a. Lowercase a will always mean a unit vector in this course. But maybe we can have unit vectors that point in different directions. So maybe we have a unit vector that points in the same direction as A. So in that case, we would say, or we would write this lowercase a with an arrow, subscript capital A, and so its magnitude is always 1. So let me give you an example. Let me just draw it here. So let's say that this thing is capital A, meaning its length is not 1, or it could be 1, but it's probably not 1. A unit vector that points in that same direction might be this. So we're saying that has a unit length, the length of 1, and so we're going to use the lowercase a to represent a unit vector, and it points in the same direction as capital A, so we're going to give that a subscript a. So that's what our notation is telling us here. Okay, a unit vector that points in the same direction as capital A. We'll always use that notation, lowercase a, for unit vector. Okay, so if I wanted a unit vector that points in the direction of A, what I could do is take vector A and divide it by its own length. Right? If I take a vector and I divide it by its own length, now it's got a length of 1. and the direction is still preserved. So I would have my unit vector that I'm after, and based on what we said about notation, I could also write something like this. Therefore, I can write, if I solve this for the vector A, I can write a vector as its magnitude times a unit vector in its direction, in the same direction. Okay, so let's continue on. So I can write then a three-dimensional vector, and I'm just using capital A, why not, right? If it's the first letter of the alphabet. I can write a three-dimensional vector as some component, so in the x direction, plus some component in the y direction, plus some component in the z direction. So we would say that ax, ay, and az, uppercase that is, are the components of vector A. Okay, so what does this mean? Well, I'm going to draw a case of this, and I'm just going to draw it in 2 dimensions because it's easier to draw in 2 dimensions. So we'll just say x and y. So let's say I have a vector. How about this guy here? Maybe it goes over 2 and down 2. So maybe my vector A looks like this. Okay, that's a vector. It has a length, right? And it has a direction. So I'm gonna specify that with capital A. It's with an arrow over it like that. Now, I went to the right by 2 units. So we're gonna call this thing here, this is little a in the x direction, right? This is a unit vector that points in that direction, x. Also, this thing here that points up 1 unit, this is a y. This is a unit vector that points in the direction of y 1 unit. So why do I need those? Well, now I can write my vector, not ay, excuse me, a. I can write my vector as it went 2 in the x direction, so 2 times ax, like that. So 2 is the component in the x direction, and then a plus, or minus in this case. So minus 2 is the component in the y direction. It went down like this. All right, so 2 minus 2 are the components of vector A, and little a x and little a y are the unit vectors that describe this vector A. Okay, now from the Pythagorean theorem, now if we wanted A, which is the length of this thing, right? So just the length A, or with bars, those mean the same thing. From the Pythagorean theorem, we would take 2 squared plus minus 2 squared and then take the square root of that. So in general, now I want to get away now from this example, which is only in 2 dimensions. In general, coming back over here, the length of A is the square root of the sum of each component squared. Right? This would be the length of any vector with components ax, ay, and az. Okay, now let's talk about how we can add and subtract vectors. So first of all, let's do addition. So let's say that I have a vector A, as I've specified up here already, And then let's say I have another vector b with components bx plus by plus bz. Now, let me pause for a second. You might ask, why am I using ax, ay, az here for b? Remember, we're always going to say that lowercase a represents a unit vector in that direction. So this is still a unit vector in the x direction, a unit vector in the y direction, and a unit vector in the z direction. So those little a's, those don't change. Those are always going to be, these guys here, pointing that way in the x direction, pointing that way in the y direction, and pointing, in the z direction. So, but what does change here is the component, right? Bx, by, bz. So if I wanted to add two vectors together, let's say vector c is a plus b. Okay, we're going to use the so-called tip-to-tail method. And so, let's say I have vector a here. There's vector a. And then maybe b points, like this. And I want to know, well, what is vector c? Well, vector c, you can imagine if I put b's tail right here to a's tip, then b would look something like this. Okay, so that's the so-called tip to tail, and then the resultant vector is this thing here. This would be c. So what I did here was I just moved b to put its tail by a's tip, and then that gives me vector c. And you can see this makes a parallelogram. Okay, so this is the parallelogram method. If you're not comfortable moving vector b to a, then you can just see that c makes the diagonal of the parallelogram, right? And subtraction, if we wanted maybe vector d was a minus b, you can look at that as adding the opposite of b. So the opposite of b, we just turn it around, right? So here's negative b. Okay, so now you're adding a with negative b. So we just talked about how to add a with b. Right? That's the parallelogram or the tip to tail method. So this would be d. Okay, so all of that is to say, in addition, we add the components. So, we took a with b here, and so we added the components. So we took ax plus bx in the x direction. Then we took ay plus by in the y direction, and az plus bz in the z direction. Okay, and then if we were to subtract, like we took a minus b, the components subtract. So ax minus bx in the x direction plus ay minus by in the y direction plus az minus bz in the z direction. All right. So it turns out, based on this definition, that addition and subtraction, or addition anyway, of vectors enjoys the usual properties, right? So we can talk about the commutative property. So, for example, vector A plus vector B is equal to vector B plus vector A. And we can talk about the associativity property. That is, if I add vector A with vector B and then take that and add that to vector C, that's the same as maybe adding vector B with vector C and then adding vector A. And then it also enjoys the distributive property. So if I took a scalar, maybe K, right, without the arrow, times A plus B, that would be as if I took the vector, or the scalar K times the vector A plus the scalar K times the vector B. Okay. Now, let's talk about position vectors. Okay, a position vector is the directed distance from the origin to a point. Okay, so let's say that we have a point P. We'll write the point like this. At a certain point, maybe in 3 dimensions, x, y, z. Then we'll write a position vector like this, r sub p. So this is a position vector to point P. It's from the origin, which we use O to represent the origin, to point P. So this is kind of geometry notation, OP. And then this would be x, right? Because the origin has coordinates 0, 0, 0. So this is still just x in the x direction plus y in the y direction plus z in the z direction. Okay, and this is sometimes called the radius vector. R, so R here stands for radius. So again, this is the position vector. And a distance vector is the displacement, meaning the directed distance from one point to another. From one point to another. So suppose then we have two position vectors, RQ and RP. So let's say we have RQ and RP. So let's say here's the origin, O, and here's the point P. Then RP is this thing. Okay, it's a position vector from the origin to point P. From to, you have to keep that in mind, the directed distance from and to. So now let's say we have point Q over here, right? So the distance vector, oops, I didn't draw that very well. Excuse me, the position vector, this would be RQ from the origin to point Q. Now what we're talking about, the distance vector is the directed distance from one point to another. So that would be, I'll draw it in blue, the distance vector is this thing here. In this case, we're going from P to Q. So what we would do is we would call this R sub PQ. And it's a vector, so we give it, the arrow above. And what we just said about addition and subtraction and so forth, we would say that this vector is equal to Q's x component minus P's x component in the x direction plus Q's y component. Excuse me, that's not right. Let me back up. So I guess the notation was Q's x component minus P's x component in the x direction. That's what I wanted. Plus Q's y component minus P's y component in the y direction plus Q's z component minus P's z component in the z direction. This should not have an arrow above it, by the way. Okay, so why is that? Well, that's this vector in blue. But if you notice, based on what we said with tip to tail and so forth, if I start at the origin and I move in the direction RP, now I'm here. Then if I add to that this vector RPQ, right, tip to tail, right, tip, and the tip is already to the tail right there, tip to tail, then that gives me vector RQ, right? Start at the origin, move along RP, then tip to tail, RPQ, that gives me exactly the tip of RQ, so that gives me RQ. So if I wanted the distance vector RPQ, this is RQ minus RP, right? And that's exactly what we did here. We talked about subtraction, how the components subtract, so we took the x component of Q minus the x component of P, y component, z component, RP minus RQ. All right, so in the next video, let's continue talking about vectors, and we're going to talk about multiplication and vector projection, which is an important operation for vectors.